A sinusoidal voltage V equal 40 sine 100t in volts is applied to a series RLC circuit with inductance L equal 160 millihenry, capacitance C equal 80 microfarads, and resistance R equal 68 ohms. Let's write down what the problem gives us. We know that the voltage provided by the generator changes with time according to this equation. V equals 40 sine 100t. From this equation, we learn that the maximum value of the voltage across this circuit is 40 volts, and the angular frequency for the oscillations is 100 radians per second. We are also given the inductance 160 millihenry, the capacitance 80 microfarads, and the resistance are 68 ohms. In part A of the problem, we need to find the impedance of the circuit. Well, this is an RLC series circuit for which we know that the impedance can be calculated as the square root of the resistance squared plus the inductive reactance XL minus the capacitive reactance XC squared. All we have to do is find XL and XC. According to the definition, the inductive reactance XL equals the angular frequency omega multiplied by the inductance L. We replace the given values and we have omega is 100 radians per second and the inductance L is 160 times 10 to minus 3 henries. Don't forget it is given in millihenries. And we obtain a value of 16 ohms for the inductive reactance XL. We calculate now the capacitive reactance XC as 1 over omega C. That is equal to 1 over angular frequency omega is 100 and the capacitance is 80 times 10 to minus 6 farads. And we obtain a value of 125 ohms for the capacitive reactance. I would like you to remember that the capacitive reactance XC is bigger than the inductive reactance XL. This will come into play when we draw the Phasor diagram. Now that we know XL and XC, we can calculate the impedance Z as the square root of resistance is 68 ohms squared plus 16 minus 125 squared. This gives us a value of 128.4 ohms for the impedance of the circuit. In part B of the problem, we need to find the maximum current in the circuit. The maximum current in the circuit is given by the maximum voltage divided by the impedance. The maximum voltage is 40 volts. And the impedance is 128.4 ohms, and therefore the maximum current in the circuit is 0.31 amps. In part C of the problem, we are asked to draw a Phasor diagram for this circuit. Now, I would like to remind you that whenever we drew a Phasor diagram, the phasors were written as a function of cosine, not sine. Therefore, we are going to convert the equation for the voltage from a sine function to a cosine function. For that, you need to remember that sine alpha equals cosine alpha minus pi over 2. In our case, alpha is nothing else than 100t. Therefore, we can rewrite the voltage as 40 multiplied by cosine of 100t minus pi over 2. We know that in an RLC series circuit, the voltage and the current through the circuit are out of phase by a certain angle, but we do not know that angle. So we can write the current with respect to this voltage as being out of phase by an angle theta, which is not the same as the phase angle. So we have the current written as the maximum value of the current, which we found out is 0.31 amps, multiplied by cosine of 100t minus pi over 2 plus an angle theta, which we will need to figure out. Also, we don't know if the current is ahead or behind the voltage. But let's just simply build the Phasor diagram. We start with the two axes, horizontal and vertical. And because this is a series RLC circuit, the current is the same through all the elements, and therefore the current through the circuit is our reference phasor. The phasor for the current is represented by this red arrow, and based on this equation that we have here, this phasor will make an angle 100t minus pi over 2 plus theta with the horizontal axis. Now let's continue to draw the phasor diagram. We know that the voltage across the resistor is in phase with the current. Therefore, this is the phasor for the voltage across the resistance. The voltage across the inductor is pi over 2 ahead of the current. Therefore, the voltage across the inductor will make an angle of 90 degrees with the current phasor. And the voltage across the capacitor is pi over 2 behind the current. And why is it that I drew the voltage across the capacitor phasor much longer than the voltage across the inductor? Because if you remember from part A of the problem, the inductive reactance XL is much smaller than the capacitive reactance XC. Therefore, the voltage across the capacitor is much bigger than the voltage across the inductor. Now, in order to find the phasor for the voltage across the entire circuit, we add voltage across the inductor and voltage across the capacitor by moving the voltage across the capacitor phasor with a tail at the tip of the voltage across the inductor. And when you add them up, the resultant vector will have the tail in the tail of the first vector, VL, and the tip at the tip of the second vector, VC. So this will represent nothing else than VL plus VC, but because they are oriented in opposite directions, it turns out to be VL minus VC. This is the resultant of the phasors for the voltage and current added together. Now we have to add this gray phasor to the purple phasor for the voltage across the resistance. We use the parallelogram theorem. We draw a parallelogram, two sides that are parallel to the two phasors. And the resultant of the two phasors will be the voltage across the entire circuit. And it represents the diagonal that starts from the tail of both vectors that you add up and ends up in the opposite side of the parallelogram. Now this phasor makes an angle phi, which is the phase angle, with the current phasor. But with the horizontal axis, the angle that the phasor V makes is 100t minus pi over 2. In the last part of the problem, we are asked to find or to write the equation for the current in the circuit as a function of time, which means we need to figure out this theta angle. So we do have the voltage written as 40 cosine 100t minus pi over 2, where this is the angle that the voltage makes with the horizontal axis. And we do have the current written as the maximum value of the current I multiplied by cosine of 100t minus pi over 2 plus theta, where this is the angle the current makes with the horizontal axis. But the phase angle, the angle between the current and the voltage, phi, is something that we need to figure out. Well, if you look at these angles, remember, the angle to the current is measured counterclockwise. The angle to the voltage is measured clockwise. Therefore, one is positive, one is negative. But if you add up these two angles, you actually get the angle phi. So we can write the angle for the current, 100t minus pi over 2 plus theta, plus the angle for the voltage, but because this angle is measured counterclockwise, below the horizontal axis, we have to add a minus sign, equals the phi angle, but again, we have to add a minus in front of this because the angle is measured from the current to the voltage. And because we have to go clockwise, that angle has to be negative. 100t cancels out, pi over 2 cancels out, and I have left that the angle theta that we didn't know equals minus the phase angle phi. Therefore, we can rewrite the equation for the current as maximum value of the current I multiplied by cosine of 100t minus pi over 2 minus the phase angle phi. Now let's find that phase angle. The phase angle is calculated as XL minus XC over R. We know XL is 16 ohms, XC is 125 ohms, and the resistance R is 68. Therefore, the value that we obtain for tangent of the phase angle is minus 1.6. Don't forget to have your calculators in radians. We get from there that the phase angle phi is minus 1 radian. Does it make sense? Yes, it does. It is measured clockwise. And we can replace this phase angle phi in the equation for the current, and then we have the equation for the current equals to 0.31, the maximum value of the current, cosine of 100t minus pi over 2 plus 1. Of course, you can always write pi as 3.14 divided by 2 and add it with 1. I kept it this way so you can see the difference between the phase angle of the voltage and the phase angle of the current. It is clear from this equation that actually the current is ahead of the voltage. This plus 1 tells you that the voltage is either behind the current or that the current is ahead of the voltage, because plus 1 is measured counterclockwise.